the comparison, more relational versus non-relational, or RDBMS, Relational Database Management System, versus this new thing that's not a relational model at all. So first of all, the SQL land came out of kind of the big box of vertical scale systems. So in other words, if your database is too slow, you're trying to put too many transactions against it, you get a bigger box. And you keep getting the biggest box you possibly can until you can't get the bigger box anymore. And of course, all the Oracles and MySQLs and Postgres and everything actually aren't really quite scalable, but this is kind of where the mentality that they grew up in. On the opposite side is, well, instead of having these big expensive boxes that are self-redundant, because I don't want that box to go down, I'm just going to go down to Walmart and I'm going to pick up the cheapest bunch of things that I can. I'm going to wire all these things together, and then I'm going to build a tolerance into my software so that if I lose nodes, I don't care. If they blow up, I'm good. Matter of fact, the attitude is, not only do I want my system to be tolerant of failures, but I want it to run and work well even though things are blowing up, right? So if you've got a cluster of 1,000 nodes, and each node has four hard drives, you got 4,000 hard drives that can potentially fail, plus 1,000 nodes, plus all the other hard drives associated with it. You're going to be replacing hardware almost every single day. And how does your software work on that? How does it deal with that kind of situation? So we have query by SQL, which is a language we know and love to hate, depending on what we're trying to do with it, if it's cooperating with us as well. And in NoSQL space, it tends to be, doesn't tend to be in the SQL. Some of them have SQL-ish type of languages with them, but a lot of times you're going to be working with a custom API on this side, or some kind of SQL-ish layer. And then, so when we're doing SQL, basically what we're doing is we're taking the information that's in our database, right? We're moving it to our application. We're going to do something useful with it. And then, in a lot of cases, we're going to put some information back, some updates or something. The opposite of that is a stored procedure where you take your algorithm instead, and you're going to put that in your database, or in your data store, and you're going to have it run locally where all the information is instead. It's really good for you to have to process a lot of stuff. On the NoSQL side, they have something called MapReduce, which is a way of taking a particular algorithm, dividing it up over however many nodes you have, running it in parallel, and then taking the results and aggregating and reducing them into some particular answer. So on SQL, we're used to do all of our ACID transactions. A lot of times you get either very, very little to no ACID or transaction support. A lot of times you do have ACID, but it's only for a single unit of work, a single quote or single get. You don't have this over multiple units of work, which is, it can be a really very, very big deal. It can be a deal breaker. It just depends on the data in your application and what you do with it, right? And then on the NoSQL side, we tend to have these eventually consistent types of transactions. This is quite a different work. On the SQL side, we have advanced indexing, we have foreign key support, we have strong blocks, all these kind of things that make our lives very easy, and the database does a lot to make sure our data is consistent and good, and all that fun stuff we want. So on the NoSQL side, a lot of times, no. A lot of times you don't have indexing, it just depends. Some have very strong indexing. Some of them indexing doesn't really even quite apply, depending on what the data store is. Same with indexing support. If you've got a document store with key values, you've got a key value, some of the stuff doesn't really quite apply. Schema. We all have our RDBMS schemas, especially when we have to write all our update scripts. We have to test them against all our development servers. We have to test them against our QA servers. We have to test them against our staging servers, and then we got to roll all this stuff into production. It's a big pain. It's a big headache. A lot of these systems support either a schema doesn't really apply, or they implement a very, very flexible schema where, if you want more columns, great, go ahead and add the columns. To the point of even referencing a new column, be able to add that new column in for you. But it's very easy to do, and it kind of avoids some of this pain that we have. So as far as APIs, you know, we have JPA, we have JDBC, we have Hibernate, we have all these fun things that we deal with. A lot of times on the other side, now it's depending, a lot of times you're going to have a custom API. A lot of times you'll have a REST API, but there's convergence. They're trying to move towards the stuff that we know and love to make it easier for us to work with, a lot less expensive to be able to implement. And then also on the access control, RDBMSs have a lot of access control. Most NoSQL data stores have absolutely zero access control. So you have to be careful. You can have anybody come in and start wiping out all your data. Certainly you don't want to expose it to the web or anything. You got a RESTful interface, and you can have anybody issue a root command or against your data. Obviously that's a very bad thing. So the last slide I have on this, SQL systems tend to have very complex on-disk representation of access. So for example, at Oracle actually would love it if you just gave it a bunch of disks that are raw, and it would handle everything for it. It can determine everything. It has very complicated random access, things that it does. It measures disk speed and spindles and all these kind of things to be as fast as it can on disk. A lot of the NoSQL stores completely cut here and just say, you know what, I'm going to make my on-disk representation as simple as possible. I'm just going to do an end-only style writes, and when I do reads, I'm going to keep an index in memory. I know where that thing lives. I'm going to do a seek, I'm going to do a read, and then I'm done. I'm going to rely more on the operating system to help me cache all this stuff and make it more efficient. So development stuff, a lot of that we talked about, multi-platform support. A lot of the NoSQL data stores, because of where the economy grew up and people who develop them, tend to be much more focused on Unix and Linux. To a little bit lesser extent, Mac, there's a lot of good Mac support, but not as much on the Windows platform. I don't mean that as a slam, I'm just saying that's where a lot of development is done. Commercial support. A lot of times that's a huge thing, especially when your company wants strong commercial support. Of course, with RDBMSs, the vendors would love to sell you support. A lot of third parties, you get us anything you want. On the NoSQL side, it just depends on the project. Some of them are actually commercial projects that have an open source counterpart or are commercial. Some of them are completely open source, and so you have whatever resources are available, different users groups or use groups or different things like that. So that's a huge consideration. And then on tool support, again, we have all kinds of tools that we work with day in and day out. On the NoSQL side, tends to be not a lot of strong tool support. Again, that's one of those things that's changing as this technology matures and time goes on. So detail. So now we're going to kind of talk about the breakdown of these four groups. Some of the specifics about what they're designed for, what they're good at, what they do, what they look like. And then on the next slide, I'll present some specific products in that space. So column stores. So these databases are going to look, at least on the surface, they look a lot like the relational databases that we work with all the time. But they tend not to really be relational. For example, Google's Big Table, which was one of the original implementations, was a really good paper out there in 2006. If you're interested in this stuff at all, that's one of the good places to start. It's called Big Table, and that's what it is a big table. You can have tens or hundreds of thousands of columns, by hundreds of millions and billions of rows. And it stores the data in a column format, so basically a big hash. And it knows how to distribute that stuff, break the hashes out, and distribute them over Hadoop in particular, which is another product, well, HBase, but anyway. But it will scale to thousands of nodes. And this is what Google uses internally to do a lot of the magic that they do. Schema list, it's actually probably more proper to call it more schema relaxed. It has a concept of what it calls a super column or a column family, which is basically a grouping of columns. There's a certain technical reason why they do that. But the columns under a particular family, you can have as many or as few as you want. You can add them as you want. And some of the interesting effects is your information in any particular column tends to be much more similar than the column across the row, especially if you've got a lot of rows. And so they can take and compress by rows, you've got, compress by column. And if you have 10,000 columns on any particular row, you're probably not doing, updating all 10,000, maybe only updating a handful. And so the way they store the information is null values are essentially free, or null cells are essentially free to store. So it can be very efficient to store this information. But one of the big differences here to understand is because the data is being stored on disk in a certain way across the columns, is it tends to be more difficult to do row-style updates. So it tends not to be as good at transactional types of things that we do on web or a lot of applications. It tends to be much better for data warehousing style applications where you have just a bundle of information and you want to be able to very efficiently pour over all that information in a very fast way, very distributed, very parallel way, and pop out some kind of an answer that's meaningful. So some of the products in the space, we have Bigtable, which is Google's. Again, there's a great paper out there written in 2006. You can Google for Google's paper, and it's got an excellent background, a lot of data information. It's actually only about 10 or 12 pages, I think. It's fairly short and not super technical, so it should be able to get through it pretty easily. Hadoop or HBase. Hadoop is a little bit different of a product. It's part of the Apache group, and Hadoop is a name kind of for this ecosystem that's out on Apache. There's probably 2 or 3 dozen different projects that form part of Hadoop, this big project. It's also the name, what they call the non-reduced part of it. But underlying it, instead of what they decided to do with this project, instead of taking this database and making it distributed, they made a distributed file system instead called HDFS. And then we're going to store a bunch of stuff and distribute it on the file system. And then from there, you can build up additional layers. And one of those layers is HBase. So it's a column store that sits on top of this distributed file system. Super popular. There's commercial support. There's huge communities. There's dozens of projects that are part of this. There's just a lot of really good stuff. Chris was talking about UJUG here, the Hadoop user groups that are coming out as a result. It's very popular. Cassandra, which was developed by Facebook, I believe, and it's Java-based. And one of the very interesting things is they have LAN and WAN replication out of the box. And so that can be something very, very important for you. If you've got distributed data centers, here's a product that kind of covers replication out of the box. One company I worked for before, we tried to do some of this with Oracle, and it was possible, but boy, was it hard, and it was, of course, very expensive to do. And you can never get it quite perfect. It was never real time. Of course, you're talking across the continent, it's never real time. Hypertable, which uses a pluggable distributed file system, so there's a few of them in there that you can run it on. Vertica is actually quite interesting. It's one of the commercial products in this space. There's a paper called C-Store, C-Store, where they talk, started out in academia as an academic paper, and then eventually this worked into a commercial product that HP now owns. And one of the very interesting things about it is how the full SQL implementation on top of it with this column store underneath. So all of your, not sure if all, but many of your business intelligence tools will work on this out of the box. A lot of the other SQL tools that we're used to working with work with it out of the box. So it kind of crosses that gap, and that's one of the things that makes it interesting. And then of course on top we have Amazon SimpleDB, which we can go out and play with and not have to install. Have Amazon do something out there for us. So document stores. There's a lot of products in this space in particular. Actually, in general, there's a lot of products that are covered in a gamut here. And at some point, there's going to be a lot of consolidation with these, depending on who's popular. So a lot of these have very good cap tuning, so you can